So I skipped chapters 1 and 2 at the beginning of the class because they're mostly stories and examples. And I think the authors of the book like to start the book that way because it sort of gets you maybe interested in what's going on. Chapter 3, histograms, chapter 4, maybe those chapters are a little bit dry. They just sort of introduce you to the actual nuts and bolts of statistics. I prefer to start with those chapters just to get that out of the way. And go back and do chapters 1 and 2 now when I feel like we can say a little bit more about those examples. Okay, so I'll do that. I'll do end of chapter 12 and then chapters 1 and 2 today, and I think that'll be about it. So I'll start chapter 13 on Thursday. So I'll post a handout on BSpace today. I haven't quite done it yet, but a handout about really chapters 13, 14, and 15, which are all about probability. So we'll shift gears a little bit. The first 12 chapters of the book all deal with data in some level, in some way, either descriptive statistics or examples and whatnot. Okay? All right, so I want to finish up the last bit of chapter 12. So I'll just remind you of the example I'm working with, the data. For midterms and finals. Okay, so this is the data. And last time I found the equation for the regression line. And I'll remind you of that calculation just quickly. I'll do it kind of my way, not the book way, but the point slope way, to find B. So to find the equation for a regression line in general, we have this form. Predicted y value is equal to mx plus b. And again, I just want to emphasize this word predicted is important. If you just said y equals mx plus b, the usual equation for a line, the implication there is that all the actual values are on a line. And it's not true that the actual values are on a line. What's true is that the predicted values are on a line. So if you have some football-shaped thing here, that's the line we're finding. The regression line is a smooth version of the graph of averages, and it is a line. But really what we're claiming, or what we're saying here, is that the predicted values are all on a line, not the actual values. OK, so how to find B? B is r times sdy over sdx, and you can think of that kind of in terms of a rise over run thing that I talked about last time. If you have a run of 1 SD for x, so like if you talk about someone 1 SD above average for x, your predicted y value would be r SDs above average. Okay, so I made just draw that little picture. Okay, so if this distance is 1 SD for x, then the predicted value for y would be r SDs. So r SDs for y here. Okay. So that's where the slope comes from. And in our example, that's 0.6 times the SD of y is 11, divided by the SD of x is 12, and that comes out to be 0.55. And then I mentioned before that if you want to find B the way the book does it, you can predict y when x is 0. Okay? So that's sort of literally what the y-intercept means in this case, in this context, is that it's the value of y that you would predict if x is 0. I'm not going to do it that way. I did it that way last time. I'll do it what I consider to be sort of the quicker, easier way, which is just to observe that the point of averages is on the line. So x-coordinate is x bar, the average of x. Y-coordinate is y bar, the average of y. And we know that if the x value were at the average, if I plug in x bar here, the answer, the predicted value, should be y bar here. And I know m, so I can solve for b. So I'm basically using this idea. Well, let me write it write it symbolically first. And now, like I say, we know the averages, we know the slope, we already found it, so we can solve for b. So we have y bar, the average final score is 70, is equal to 0.55 times the average of midterm is 71. And then solve for b, we get 31. Okay, so finally the answer is that, okay? Predicted y is equal to 0.55 x plus 31. Now the book often will actually write out what y and x are. So the book might write this as predicted final score is equal to 0.55 times midterm score plus 31. I don't really care if you do that as long as it's clear what you mean by y and what you mean by x. So in this context, it's pretty clear. We're predicting final score from midterm score. Okay, so any questions there? That's what I did last Thursday, basically, or some of what I did last Thursday. Okay, so now I wanted to talk today a little bit more about why we would want to find the equation of the regression line, what we might do with it, and a little bit about interpretation of it. So say uses and facts. So first one I mentioned very briefly is that if you wanted to do many predictions, you might want to find the equation for the regression line, and then anytime you want to do another prediction, just plug in an x value, you get out a predicted y value, and that would be a little bit faster than performing the regression method over and over again. The information you get here agrees with the regression method. If I do the regression method, my answer should be the same. It's just a little bit longer to do the regression method over and over again rather than using the line. Okay, so useful if making many predictions. And I wanted to talk a little bit about how to interpret this. Now, the regression line, in some sense, is an extension of the ideas of descriptive statistics. It's a line that attempts to find the graph of averages. So you're trying to find the average y value corresponding to each x value. And that's, like I say, sort of an extension of summary statistics. In addition to that, the regression line is often used to try to establish or get an idea of the effect of x on y. Okay, so often people will call x the independent variable and y the dependent variable, sort of implying that there's some natural reason why x causes y to be different. And that's often a mistake. So it could be that changing x would change y, but we don't really know that. Okay, so I'll do a couple of examples that sort of get at illustrating that. The first one is using this data. Suppose we have Alex and Bobby take these exams, and Alex does 10 points better on the midterm. So then my question is about, well, I guess even before I ask the question, the question I'm about to write, so if Alex does better on the midterm, you should expect, I think, or guess that Alex will probably do better than Bobby on the final. So then if you're a statistician, you like to attach numbers to things, you might then try to sort of wonder about how many points about how many points better would you guess Alex will do on the final? Okay. So again, I think it's natural at least to guess that Alex will do better. But then you might wonder How much better? So any thoughts on that? Guesses? Can we answer the question? Yeah.
I'd say 6 points because of the 0.6.
Maybe around 6 points. Thinking about the correlation of 0.6. Yeah, it was another 5.5. So where's the 5.5 come from? From the slope of the regression line? Any other thoughts? Does it make sense to answer the question? I mean, can you? Is it reasonable to try to get a number here? So I think it is reasonable to try to get a number here. And 5.5 is the number that I would use. It's sort of similar to using the correlation, but one thing you might think about is these, in general, x and y might have very different units. So it's not going to make sense, for example, if you have, say you're trying to guess someone's, well, I'll come back to that. I'll come back to why 0.6 maybe doesn't make sense when I talk about my next example. Yeah, I think the context will make more sense for the next one. In this one, the units are almost the same, right? They're points, and the SDs are about the same. So points, I think using 0.6 isn't so obviously wrong. But the answer is 5.5. Might be more, might be less. One thing you notice here is that I didn't tell you what their actual midterm scores are. I don't need to, because it doesn't really matter. If there's a linear relationship, just by a rise over run kind of argument, if the run is 10.5, right? Or sorry, if the run is 10, just kind of think rise over run is 0.55. If the run is 10, then we'd sort of predict the rise would be 5.5. So run equals 10, rise equals 5.5. And this is not, I'm not trying to say this is going to be exact. This is again talking about predictions. So the prediction for Alex will be about 5.5 points more than the prediction for Bobby. Okay, it might be that Bobby does better on the final. I don't know, right? But this is sort of typically, or on average, you should expect about a 5.5 point differential. Okay, questions on this? Okay, so I want to contrast this with another example. Which is for height and weight. Or I'll write it as weight and height. I'm going to make weight the x variable. So positive correlation, there's a regression line. I'm not going to give actual numbers, but I just want to sort of think through this. Suppose I eat, just to make it a nice round number, I'm going to make it 10 pounds of ice cream. I'm not saying that I could, just saying suppose it happened. So I come back Thursday, and I've gained 10 pounds. And my question is, can we use slope of regression line to predict how much taller I get? What do you think? If I do this, if I gain 10 pounds, would you guess that I'm going to come back taller? No. So there's not that sort of, there's not, what's the difference? What's the difference between these two examples? Yeah. Okay, so he mentioned the regression fallacy. This is different than the regression fallacy. His main idea is right, which is that changing x does not guarantee a change in y. Okay, so in this case, there's no particular reason to believe that if I gain 10 pounds, that I will get taller. Yeah. Yeah, so one common thing you'll see is some statement like this, that correlation, or sometimes you'll see association. So correlation is linear association, okay? So association in general just means two things are related. Correlation means that they're related in some linear way. Correlation does not imply causation. Sometimes you'll see that shortened to association is not causation. It's a pretty common mantra for statisticians. To just sort of be aware that just because two things are associated or correlated, that doesn't mean that they're necessarily, that there's a causal relationship, meaning that changing one will make the other one be different, okay? So we talked a little bit about this idea in the context of Berkeley High School with incomes and grade point average. And I gave you a little bit of a silly example of shoe size and reading ability for elementary school kids, right? That you know, kids are, so older kids tend to have bigger feet and tend to read better, okay? But if you read a lot, that's not going to make your feet grow. If your feet grow, that's not going to directly cause your reading ability to increase. You know, if your feet are growing because you're getting older, well then sure, you know, you're probably in general going to read better, but it's not because of your feet, right? So yeah, so correlation does not imply causation, even though there's a correlation in those cases, doesn't mean that there's a causal relationship. So same thing here. It applies to both of these cases that there's not necessarily a causal relationship, okay? The one thing that makes this different is this is talking about making a change for an individual, right? Changing something for an individual here, we should not expect a change in y. For the other example, we're talking about two different people. So to make this problem or this example more like that one, you might say, well, suppose, you know, there's me, and let's think, like, imagine you don't know anything about me, you've never seen me, all you know about me is my weight, okay? And suppose there's someone else that weighs 10 pounds more than me. You don't know anything about them except for their weight. Now, in that case, you would expect the person that weighs more than me, on average, they're probably a little bit taller, okay? If you don't know anything else about them, just their weight, you know, like I said, you've never seen us, that you might guess in general, you know, heavier people are taller, so you might guess, and it would be okay to use the regression line to predict about how much taller that other person might be compared to me. But like I say, it's not reasonable to kind of intervene and change my weight, either like I go on a diet or I gain weight or something. You shouldn't expect that to change my height, right? So the general statement is true that heavier people tend to be taller people tend to be heavier, so it is reasonable to use the regression line to predict differences in that way, right? Just like I did there. I know there's this difference of 10 points between their midterm scores, so it's reasonable to think that, you know, in general, Alex probably will do better on the final, and about 5.5 points is a good guess for how much better. If, for example, you know, the class ends and then, you know, grades are being submitted, and then Alex looks back at the midterm and turns out that points were added incorrectly, should have gotten 10 more points, then maybe in that case, that's not going to change the final score, right? So just because there's, again, because there's this association, if you change x, you shouldn't necessarily expect y to change, even though in general up there, people who do better on the midterm, in general, do better on the final. Here, heavier people tend to be taller, but you can't like change x and necessarily expect y to change. So that's what this is getting at. Okay, questions on that?
Talking about longitudinal versus
Okay, so her question is about longitudinal research. Can you then use the slope? Well, so longitudinal data is data that follows individuals over some period of time. Cross-sectional data is data that sort of takes a snapshot of everyone, kind of how they are right now. I think what she's thinking about is there's an example in the book that looks at height of people of different ages. Maybe I'll draw a little quick sketch of this. So you have height starting, so you have age starting at 0, 10, 20, 30, 40, 50, 60, 70, 80, say. Okay, so let's say we're talking about adults. So they're roughly between ages of 20 and 80. There's a pattern that often is true that, now this is like if we just looked at everyone's heights today, for example. So that would be cross-sectional. So there's a pattern that, I don't remember exactly what it looks like, but something roughly like this. Okay? And I don't know what these heights are, but there's this sort of downward trend. And this sort of makes you think that people get shorter as they get older. Right? The older people here are shorter than the younger people. That's not true. So we have age here, we have height here. Okay, there might be people might shrink a little bit because they have some compression of their spines or stuff like that, but that's not what's going on here. What's going on here is that the older people were born earlier, and there are, I think most importantly, dietary effects on height. So these people, the 80-year-olds, grew up, born in 1930. Their diets weren't as good as the people that were born in 1990. Okay, so because of that, the people that are 80 now never got as high, never got as tall as the people born more recently. Okay, so that's the effect that you are really observing here. It's not that people are getting shorter over time. So longitudinal data looks at individuals over time. So longitudinal data with age or something like this would not show the same thing. Okay, so to address the association causation point, you still have to be a little bit careful. You can't necessarily say that there is if you observed that, if this data were longitudinal, okay, if this data were longitudinal and we started collecting data, I guess what would it be? It would be 60 years ago. So I guess if we started collecting data on 20-year-olds in 1950 and looked at them over a course of 60 years until now, if this picture still looked like this, then there should be some reason, but it's not necessarily clear that age is that reason. Okay, it might be that something was, I don't know. It's hard to find an explanation for this because it shouldn't happen, but maybe there's something put in the water, an additive was put in the water here, and people started getting smaller, or something. There would have to be something strange to force people to get smaller, but it might not be the aging process itself. There might be some other explanations. You still have to be a little bit careful, but at least if you have longitudinal data, you eliminate this problem that you're looking at different people. So with cross-sectional data, they're born at different times, they have different diets, other things are going on, okay? So yeah, longitudinal data doesn't solve everything, but it does help at least for something like this, okay? Okay, any other questions? This idea? Okay. So if you have data from a well-run experiment, and there's some examples. There's at least one good example in the book. And for now, I'm going to be a little bit vague about what I mean by a well-run experiment, and I'll talk more about it in chapters 1 and 2. If data comes from a well-run experiment, we can establish a causal relationship. So just very briefly, if I did some experiment with the effects of ice cream on height, and suppose I so suppose sort of ideally I select half the class randomly and force you to eat 10 pounds of ice cream, and I force the other half of the class not to eat any ice cream, and then we come back on Thursday and see if people change their heights, and suppose just hypothetically, it's obviously unrealistic, suppose the people that ate ice cream actually did get taller. Okay, so then we can establish a causal relationship, and we can use the regression line to determine the effect of ice cream on height. All right. So if everything is sort of well run, and like I said, I'll talk about that more in the context of chapters 1 and 2. But if you do have something like that, then you can establish that kind of causal relationship. And there are lots of examples where you can and where you can't. So I'll talk just briefly about two. One of them is discussed in your book. And it's sort of like a real experiment where they have, they look at a spring and put a weight at the bottom of the spring. And they put different sizes of weights on the bottom of the spring, and heavier weights make the spring get longer. Okay? So then you graph the points of like the weight and the length of the spring, and you see that more weight means the spring gets longer. So if you do something like that, then you can establish the effect of weight on the spring and see just how much the spring will get longer for every extra pound that you put on. Okay? So something like that, that's an example of a good experiment. Like I said, that's discussed in your book, so you can look at that if you want. And that's sort of a real physics experiment. Another example I think is kind of interesting historically is thinking about what effect smoking has on people. So smoking has a variety of effects, and you sort of know smoking's bad for you. Well, how do we know that? Well, people that smoke don't live as long. So there's one way to think about it. And then you might think about, well, what do they die of? You can look at data on smoking, and you might think that lung cancer is like a lot of why they die. Turns out that the main reason why smokers don't live as long is heart disease. Okay, so if you smoke, you're damaging your lungs, but what do your lungs do? Your lungs bring oxygen into your bloodstream. Well, if your lungs aren't working as well, it makes your heart work harder. Okay, so a lot of what happens, a lot of why people die is because they have heart failure in some way, not that they die because their lungs actually fail. Okay, the lungs are just sort of not working as well. So this makes things a little bit hard to now we know, but 50 years ago or so, this was sort of a little bit of an open area of research, that it was not entirely clear that smoking was bad for you, how bad it was, and why. Basically because of this idea. We observe that people who smoke don't live as long, but it's a little bit unclear why. And the tobacco industry and other people said, well, most of the people are dying from heart disease. They're not dying from lung problems. So why are you blaming smoking? Maybe you should blame the fact that the smokers don't have as good diets, they don't exercise as well, they drink more alcohol, they do all these other things. Maybe it's not smoking's fault, Maybe, and it's true. There are all these other possible explanations why the smokers might be dying more. They also engage in a lot of other unsafe behavior in general, or kind of on average. So when you do want to try to establish a causal relationship here, you have to be a little bit careful. You can't run an experiment for smoking, right? I can't randomly divide the class up into two halves and force half of you to smoke for 10 years and force half of you not to smoke for 10 years and then see what happens. The way probably I can't do that with ice cream either, but it is difficult to get experimental data on humans for a lot of things like that. So the thing that happened that eventually resulted in warnings on cigarette labels and things like that, and that was in the late 60s, I think, was that a few things. One was that people looked at what happened to you depending on how you use tobacco. So if you chew tobacco, you tend to get cancer in your lips and your gums, in your mouth. And if you smoke cigars, you tend not to inhale the smoke as deeply into your lungs, so you tend to get cancer in your upper respiratory system. If you smoke a pipe, you tend to inhale the smoke more deeply, so you tend to get cancer lower down in your lungs. And so based on the location of the cancer, this is a little bit how they pinpointed that smoking is really bad for you. Okay? They also did experiments on lab rats. So they exposed them to nicotine, tar, and whatever, and then dissected them after they died. So regardless of whether you think animal research is good, bad, whatever, that's part of how they kind of determine these things. So that's part of how we determine a causal relationship in kind of a tricky situation like that. Okay? All right, questions, thoughts? Okay, so one last thing I want to say about chapter 12 before I move on to chapters 1 and 2 is a kind of technical statement, and I mentioned this last time, which is that amongst all lines, the regression line has the smallest RMS error. Okay, so if you remember last time when we talked about chapter 11, RMS error, for regression, RMS error is equal to square root of 1 minus r squared times the standard deviation of y. And I mentioned just for comparison that if rather than using the regression line, we used a horizontal line through the average. Okay? So for regression, we're using some line that's roughly like that. I could, if I wanted to, make all my guesses on a horizontal line through the average. Okay? And anyone remember what the RMS error is for that line, or think about it? Yeah, it's the SD of y. So the reason for that is that if I have lots of dots here, for each dot, the prediction error is a deviation from average. Right? The line itself is the predicted value. So if I have a point here, and I want to know how far off I was when I guess, when I guess the average, and my point's actually there, the deviation from average is my error. The RMS error is defined as the RMS of the prediction errors. So I'm kind of literally calculating the RMS of the deviations from average if I make all my predictions on that line. So that's the SD. So you can see this is, in general, this is better. It's possible that they're equal when the correlation is 0. And in fact, when the correlation is 0, the regression line is a horizontal line through the average. Okay? But for any other correlation, this is actually better than guessing the average. And in fact, it's better than any other line you could draw. So there's a horizontal line through the average. Maybe a stupid line would be kind of up here or something. If I wanted, I could make guesses up there, but they're going to have, that line is going to have large prediction errors. Especially if my actual value is down here, it's a really big error. Okay? So that would be a very bad line. At least something in this general area will do okay, but this is the best. The regression line is the best. So this is our justification of why we do regression, essentially. So I think one way to think about this intuitively is that the regression line is attempting to find the average value in every strip. So if I have an x value, well, best guess I could make is the average y value corresponding to that x. Okay? And the regression line is attempting to do that. It's attempting to find the average for y value for every x. Okay, questions on that or anything else? Okay, so that's end of chapter 12. So I want to do chapters 1 and 2. It's a little bit early, but I guess it's a pretty good time for a little break. So let's take a little break, and then I'll talk about chapters 1 and 2. Okay, let's get started again. Okay, so chapters 1 and 2 kind of go together. So I'm just going to kind of lecture on both of them all mixed up together. In terms of you studying, for the I guess the midterm is 3 weeks from today. I'm not going to really cover everything in those chapters. So and I'll discuss this later as we get closer. But basically, everything you really need to know is in section 1 of the first two, section 1 of each chapter, and the reviews. So a lot of it's just like knowing the words, knowing the jargon, and I'll go over that today. As I said before, most of both chapters is examples. So I kind of recommend reading them just to get kind of a deeper understanding of what all the words are and how to use them and all that kind of stuff. I think the examples are somewhat interesting. But I won't hold you responsible for knowing the specifics about any of the examples in the 2 chapters. Okay, so yeah, so like I said, you can read them, but you don't need to know anything specific about those examples. Okay, so what I wanted to do is first just start off by defining a bunch of things. So I've talked a little bit about experiments here in the context of chapter 12. So I want to say a little bit more about that. Controlled experiment. I'm sorry, let me just say, it's chapters 1 and 2. So some of these terms, controlled experiment, so in a controlled experiment, investigators, like the researchers, the people running the experiment, decide, and this could be done randomly, so I'll say perhaps randomly, who gets the treatment, and who doesn't. Okay, and when I say treatment here, I sort of mean anything you could do to like possibly affect something else. So in my examples I was talking about here, ice cream could be the treatment. Give a bunch of people ice cream, see if they grow or not. The treatment could be smoking. See what happens to people if they smoke. It could be something beneficial, could be something harmful. It doesn't really matter. So in this context, we're just talking about something you might, do or give to people or whatever. Some drug that you think might have a beneficial effect, whatever. Okay, so that's a control experiment, and I'm going to contrast that with what's called an observational study. And in an observational study, the subjects decide. So when I say subjects, I just mean the people that get the treatment or not. So if it's smoking, people decide whether or not they're going to smoke. Okay. So going back to the smoking example, that's an observational study. You can't do a controlled experiment on people with smoking. You can't, decide who smokes and who doesn't. So the subjects in that case for smoking, they decide not only whether or not they smoke, but they also decide how much. So not only decide who gets the treatment, I'll say, and the level of treatment. So that basically the amount of treatment did they get. Okay, for some things it may be like either they get it or they don't, but for something like ice cream or smoking or something, people would decide how much they do. Okay. Okay, so in the context of a controlled experiment, if it's well run, and I'll talk more about that later, that's where we can try to establish a causal relationship. In an observational study, it may be very tricky to try to establish a causal relationship. So let me write down a few more terms. Treatment group is the group that gets treated. Sort of maybe a circular definition, but just to make it clear. So group that gets treatment. And that's generally compared to a control group. And what happens to the control group can vary. You might do nothing to them, but whatever it is you do to them, they don't get the treatment. Okay, so control is the idea is that it's kind of controlled, they're sort of left alone, and then you compare the group that gets the treatment and you look at the difference. Okay? So like I said, you can't do this in general with a lot of things like smoking, right? You could do something like this with, I don't know, a drug that might reduce the risk of heart disease or something like that. Kind of randomly, maybe give half the people the drug, leave the other half alone and see what happens. Okay, so let me write down a couple more things and then I'll talk a little bit more about this. So a placebo is something, I'll say it this way, something hopefully indistinguishable from treatment. And this is given to the control group. So the reason why this is given to the control group in many cases is that you don't want them, if you don't want them to know if they got the treatment or not, okay? So what's called a placebo effect is the effect of just getting something, right? So the problem is that if you give people like something that has no real effect, okay, they may feel better, okay? So if the thing you're measuring or looking at is something like whether or not they have a headache or something like that, if you give them something that actually is completely neutral, that doesn't do anything, they still may think it works, okay? So because of that, you don't want people to know whether or not they got something, because if they just the thought that they got something may cause them to feel better, okay? So that's often done, to give a placebo somehow. Some things you can't really do it, like you can't really have you can't really have placebo smoking. You sort of know if you smoke a cigarette or not, but you might be able to have like test something based on nicotine or tar and give a pill in the treatment group and also give a pill in the control group and make it so that people don't know if they're getting a real treatment or not. So yeah, so if you're testing a drug or something like that, that's a pill or maybe an injection, something like that, you can give a fake injection of something that doesn't have anything active in it. So obviously something like surgery, you can't have a placebo surgery, but you could do a lot of things that well, I guess you could, but you probably wouldn't. Just cut someone open and then sew them back up and say, you should feel better now. Okay. All right, so continuing on this idea, this idea of not knowing which group they're in. When we say double blind, we're talking about two kinds of blindness. And blindness is not having to do with sight, but I'm talking about whether or not the people know if they're in the treatment group or the control group. So there's subject blind, which is achieved often by using a placebo. So subject blind means that the subjects, the people that are getting the treatment, don't know which group they're in. And what's often referred to as like evaluator blind or researcher blind or something like that means that whoever is measuring the response doesn't know which group. Okay. So yeah, so sometimes it's more important than others. So sometimes the response may be something like feeling better. And it might be that the evaluator asks questions in a different way to people that got the drug and people that didn't. They may be happy and cheerful when they talk to the people that got the treatment, and they may tend to be sort of sad or whatever when they talk to people that got the that were in the control group. And that might change the responses, that make people feel better more if the evaluator knows and biases the results somehow. Okay? So ideally, the subjects don't know which group they're in. The evaluators don't know which group the people that they're evaluating are in. For many cases, this doesn't matter. Like if you're talking about like seeing whether or not people die, there's no subjectivity there. So it doesn't really matter if the evaluator knows whether or not you smoked, if they're just looking at whether or not you're dead. Okay? But for some things, it might make a difference. Okay. Okay. And let's see. Two more things I want to write down. So confounding factors. Now this is something we've actually talked about before. I just haven't called it this. A confounding factor is a third variable associated with both treatment and response. Okay. So the example with the kids with shoe size, shoe size and reading ability, age is a confounding factor. It's a variable that's both associated with shoe size and also associated with reading ability, and it explains this relationship. So a confounding factor is something that kind of confounds or confuses the issue that you're looking at. If you wanted to eliminate a confounding factor in the context of that example, you might look at kids that are all the same age and see whether or not the kids that are all the same age, for the kids that have all the same age, do the kids with bigger feet read better? And you probably see no relationship, right? So a lot of times you can eliminate confounding factors. Another example is it's been observed that people who drink coffee are more likely to get lung cancer. So the reason for this is that coffee drinkers, on average, are more likely to be smokers. Okay, so the people that are drinking more coffee, on average, more likely to be smokers. Smoking is the confounding factor that explains the lung cancer. If you wanted to actually determine whether or not coffee causes lung cancer, you might look at all non-smokers. Okay, so get a data set of coffee drinkers, none of them smoke, and then see, well, do the people that drink coffee or drink more coffee, are they more likely to get lung cancer? And you would see that they aren't. Okay, so that's confounding factor. And last thing I'll just squeeze in here is randomization. So randomization is often used to decide who gets treatment. Okay? Often used to decide who gets the treatment. So this is in the context of an experiment, right? Control experiment. Investigators decide, like I say, perhaps randomly, who gets the treatment and who doesn't. The reason why randomization is often used is that if you allow humans to decide, humans may systematically do things in some way that is undesirable. So they may tend to make all kinds of mistakes. They might choose older people, younger people, healthier people, sicker people, whatever, to be in one group as opposed to the other. And they may be unaware of the fact that they're doing it. Okay? So for that reason, randomization is often used. And you might randomly get like more healthy people or more sick people in one group or the other. But the thing is that statisticians are used to dealing with randomness and used to sort of getting an idea of, well, we observe this difference. Do we think that this could have happened just randomly, that all these extra smokers died, for example? Okay? So because statisticians are used to dealing with randomness, and we will later in the class deal with a lot of stuff like that towards the end of the class, that's sort of okay. Like we know how to deal with that. The problem that we have is that if there's some systematic kind of invisible way in which sicker people or healthier people are getting into one group or the other based on the decisions of some human, then it's a problem because we don't have a way of trying to get a handle on how much of a difference that might make. Okay, so that's, like I said, that's essentially why randomization is used. And I'll just say, ideally, no difference between treatment group and control group. Except for the treatment. Okay, so this is essentially what we're attempting to achieve by doing an experiment. And it kind of goes back to this. If data comes from a well-run experiment, we can establish a causal relationship. So this is, bottom line, this is what we're trying to achieve by having a well-run experiment, is there's no difference between the treatment group and the control group except for the treatment. And if you do assign the treatment and the control group randomly, at least there's no systematic difference. There may be slight random difference, but at least there's nothing systematic, no confounding factors. Okay, questions about that stuff? Okay, so that sort of gets us through all the definitions and terms for the first two chapters. So I'm going to do a sort of a long example. Anything else I wanted to say here? Okay, I think that's it. Okay, questions before I get into an example? Okay, so this is an example from your book. I like doing it because I think it's a good example, and also I think it's sort of interesting historically. Has to do with the polio vaccine. So polio vaccine was originally developed by Jonas Salk, and this experiment, first experiment was done in 1954. And this is not quite the first example of anyone doing vaccination, but it's the first that was really this widespread and done this well. So this is data that's from the National Foundation for Infantile Paralysis. So polio, what polio does to you is it can paralyze you, and it primarily affects kids. So infantile paralysis, that's why that's who studied this. And I don't know if you know about this about polio. Polio is sort of a widely accepted success story for vaccination in that polio has been pretty close to being eradicated worldwide, and hasn't quite been killed off, and has made a little bit of a resurgence because people don't vaccinate as completely as they used to. So you may know something about controversy about vaccination. So Yeah, so polio vaccine has been more and more, like people sort of don't bother because there's hardly any polio. The chances of getting polio are so small that if parents are not going to vaccinate for something, they might decide not to vaccinate for polio. So anyway, I don't think I'll get into that controversy. I might accidentally say some things that someone might find controversial, but I'll try not to. So let's look at the data. I guess I'll be controversial to the extent that I'll say, you know, I'm a dad and I have mixed feelings about vaccines. I'll say that much. Okay. So the data. Sorry. Describe the groups. Okay, so basically what they did in this experiment is what they sort of wanted to do was vaccinate all the second graders. So what actually happened was, like all medical experiments, you have to ask the kids, or the parents of the kids anyway, if they want the vaccine or not. Okay? So what happened was they asked all the second graders, do you want the vaccine or not? And some of them said yes, some of them said no. So I'm going to say control group in quotes here for the first and the third graders. The idea was for the first and the third graders that they were just going to leave them alone, okay? So they didn't give them placebo, they didn't do anything. They just left those kids alone. And obviously this is a very big experiment, right? So big experiment like this, it's expensive and it's a little bit hard to do everything just the way you might want, okay? So maybe ideally they would have given them placebo, but they didn't in this case. They just left them alone and sort of said, well, we'll just see what happens to them and see what their polio rate is. And polio, even then, was pretty rare. So the rates are per 100,000. So if you want, you might think of this as being kind of like percent, okay? But percent means per 100, or out of every 100 people. Per 100,000 is, rare, more rare. But it is a rate. Okay? So that's what they saw. So I guess first question, if anyone wants to answer it, is just, or so the first thing you might think about is just, did it work? Do you think it worked? Any thoughts or comments? Yeah. The rate? Yeah, so 25 per 100,000 means that it's sort of like percent, right? So it's not 25% because that would be a really high rate of polio, but it's per 100,000. Does that make sense? So it's like 0.025%, I guess. Move the decimal point over 3 places. Does that make sense? So per 100 would be percent. Per 100,000 is, decimal point is 3 points over. So yeah, so if you want, you could think about this as 0.025%, 0.054%, 0.044%. Okay? Any other questions? Yeah.
About the grade, so like the 1/3, is that like a third of the second graders?
Sorry, that's first and third graders. Yeah, I'm sorry. Yeah, so that's not a fraction. That's first and third graders all together in the second group, right? So second graders were asked if they want the vaccine or not. If they consent, they get into the first group, they get vaccinated. If they don't consent, or the parents don't consent, they're in the third group, and they don't get the vaccine. The second group is mixed first and third graders. They didn't ask them, they just left them all alone, and you can see the rate they got polio at. Yeah?
Were there equal numbers of first and third graders?
I don't know the answer to that question. He asked, are there equal numbers of first and third graders? I don't know. They're probably close. But I don't know. They're all at a bunch of different schools nationwide. So they didn't I mean, just in general, you'd think they're about the same number of first and third graders. So I think there were. They didn't do anything to sort of weed out any first or third graders. So. Okay, any other questions, thoughts? Yeah.
What if the second graders, the families, by them choosing what group they're in, if they're treatment or the control, I guess, wouldn't that be a confounding factor?
Okay, good. So let's think about possible confounding factors. So first one she mentioned is consent, basically. So the second graders, essentially the parents choose whether or not their kids are in the first group or the third group, right? So in a sense, this is like a little bit of an observational study in here, okay? It's not purely experimental. It's not purely a controlled experiment because the experimenters were not able to decide if the kids would get in the first or the third group, right? Okay, so consent is an issue comparing first and third, and also to some extent comparing the first group and the second group even, right? Because the first group is made up entirely of kids whose parents consented. The second group, so if you consider like parents who are likely to consent, if you consider them to be sort of different than other parents, they've kind of segregated themselves into the first group, whereas the second group is kind of everybody all mixed together. So kind of hypothetically, consenters and non-consenters mixed together in the second group. Okay. So this is possibly an issue, most obviously I think in comparing the first and the third groups, but also in comparing the first and the second groups. Okay. As a possible confounding factor. It's associated with the treatment. It's unclear whether or not it's associated with the outcome of whether or not they got polio or not. Okay, we'll talk about a little bit more about that later. Okay, anything else? Any other possible confounding factors? So basically, when you think confounding factors, you're trying to address this question. Ideally, there's no difference between the treatment group and the control group except for the treatment, except for the vaccine itself. So the first group is the treatment group. And really, either one of the other groups you could consider on some level to be a control group. They didn't get the vaccine, so they didn't get the treatment. Okay? So we can compare the first group to either one of those second group, either the second or the third group. Yeah? Age. So age is a possible confounding factor comparing the first and the second. Same ages for first and the third group, but yeah, between the first and the second, that's potentially an issue. I'll talk a little bit more of that in a bit. Yeah?
The third group have limited herd immunity compared to the second group.
Yeah, okay, so he said herd immunity. The idea of herd immunity is that if everyone around you is immune to the disease, you're unlikely to get it regardless of whether or not you're vaccinated because you're not exposed to it. So he said, comparing, I think, the second and the third group. Is that what you're saying? So those are both unvaccinated. And so the point is that the third group is mixed in with a bunch of vaccinated kids. So I think he's comparing the 54 and the 44 and suggesting that possibly that 44 is lower than the 54 because they're surrounded by kids that are vaccinated. Is that what you're thinking? Yeah. So that's not really getting at the treatment versus control explicitly, but it's interesting and worth thinking about, I think. So if we compare the second and the third, there's another sort of thing going on there. Okay? Anything else? Yeah.
I just had a question about that last relationship. The 44 is only 10 lower, but the second group is much larger population. So you would have the higher rate. Oh no.
It's rate.
Okay.
Yeah. So yeah, good. I'm glad you brought it up. The second group is by far the biggest, right? But since we're looking at rates, it's sort of irrelevant. The group sizes are sort of irrelevant. You know, if you think about percents, like if you have some percent chance of getting polio, it doesn't matter if you're like, you know, looking at like all of California versus Rhode Island or something like that. The rate is what we care about. Okay. So any other questions or comments? Any more confounding factors? So one I sort of mentioned, which is placebo. So no placebo was used. So that's relevant for first versus either second or third. So that the kids knew whether or not they're vaccinated, okay? Now, okay, let's see. Is that all I wanted to say here? Sorry, let me. Okay. Okay, any other thoughts, questions before I get into these a little bit more specifically? Okay, so I want to talk about these last, well, it's 2 and 4 on this list. So 4, the placebo effect. Can anyone see why that might make a difference? I guess there's actually two kinds of blindness, and neither one of them I don't think should make much of a difference. So the evaluator blindness really shouldn't make a difference. You can sort of tell whether or not kids have polio, and it's probably not a subjective decision, okay? So, yeah?
Well, if parents know that their child has gotten the vaccine, maybe they won't be as careful.
Yeah, so there's a suggestion that if parents know that their kids have been vaccinated, they might not be as careful, okay? With polio, well, what's risky behavior? Things like going to public swimming pools, that's somewhat risky in terms of getting polio. Exposure to other kids in general is slightly risky. It's generally thought that that's not a big deal for polio. If you were developing an AIDS vaccine, that's probably a pretty big deal. If you know whether or not you've been vaccinated, that might really change what behavior you engage in and change your risk level. So for something like developing an AIDS vaccine, you want to be pretty careful to give a placebo to make sure that no one thinks they're vaccinated. They all think they might be vaccinated and they don't really know. So they all sort of behave the same. So like I say, it's thought not to make much difference. But you could do it, right? You could give them all, a saline solution is often injected as a placebo for something like this, and you could do it. In fact, we'll look at some other data where they did do that. Age not thought to generally make a difference. It's possible that there might be somewhat of an epidemic or something in one grade that doesn't affect the other grades. But that's generally not thought to be what's going on here. Herd immunity may make a small difference, but again, it's not really relevant for the comparison we're interested in. It's not really relevant for comparing the vaccinated group to either of the other groups. Okay? All right, so I want to show you some better data, and then I'll talk about the consent issue. Okay, so there's another, after this experiment was done, some people looked at it and were like, well, there are these confounding factors. We can't really tell exactly what's going on, so let's do another experiment. And what they did was kind of the gold standard of experiments, which is to do a randomized, controlled, double-blind experiment. Okay, so let's give you the numbers. Okay, so we have these three groups, and oops. They mixed everyone, all the first, second, and third graders, they mixed them all together, okay? So there's no possible age thing going on, so I don't even need to write it down. This group is what we'll call the treatment group. they got the vaccine. The second group is the control group. They got a placebo. And the third group did not consent to be in the experiment. Okay, so they did not consent to get anything, and they were not given a vaccine. They weren't given anything. Okay, so basically what they did is they took all the kids, I guess 750,000 kids, and they asked them all, do you want to be in this experiment? If you're in the experiment, what's going to happen is that you have a 50% chance of getting the vaccine, you have a 50% chance of getting the placebo. So that's always the way medical experiments go, is they have to tell you what might happen to you, right? They don't have to tell you if you got the vaccine or not, but they have to tell you, you'll either get the vaccine or you'll get a placebo, and we're not going to tell you which one, okay? So in the experiment run like that, 400,000 parents, the parents of 400,000 kids agreed, 350,000 did not agree, no consent. Half of them got the vaccine, half of them got the placebo, and then this is again rate per 100,000. And now we have this. Okay, so let me just say we've eliminated 2 and 4, and 3 also. Okay, we've eliminated all 3 of these last ones. And we've eliminated consent in a comparison of the first group and the second group. These are all consenters. Okay, all the consenters are in either group 1 or 2. So when comparing groups 1 and 2, none of that stuff is relevant, right? They're all people that consented to be in the experiment. They're all mixed ages. They're all mixed around with kids with the same level of immunity. And there's a placebo. So none of those confounding factors are issues. This is a really, kind of honest attempt to figure out what the effect of the vaccine was. Okay? Any thoughts about, I actually do have some things to say, so I realize it's close to time to go, but I am going to keep talking. Anyone have any thoughts comparing these 3 numbers to those 3 numbers up there? Notice anything? A couple things you might notice. You might compare this 28 to the 25, and that's a reasonable comparison. Those are all people that consented and got the vaccine. The ages may be a little bit different, but basically those are about the same, and you can see that the numbers are about the same, 28 here, 25 there. This last group, these people didn't consent, they didn't get the vaccine. That's comparable to the third group there, no consent, no vaccine. Again, this is just second graders, so maybe there's some small possible effect there. But basically the first and the third groups here are the same as the first and the third groups there, and they have about the same rate of polio. The 71 here is bigger than anything we see anywhere else, right? So what's going on there? Any thoughts? Yeah. Yeah, so there were some parents that looked at this and thought what he thought, which is, what's in the placebo? Because these are kids that didn't really, they didn't get anything except for the placebo. You sort of just left them alone. And you compare that to the people that didn't consent. The people that didn't consent have a much lower rate of polio. So that's maybe troubling. And that just sort of doesn't show up there, right? There's no placebo up there. So that might bother you. What's really going on, the placebo was just a placebo. It really wasn't doing anything bad. What's really going on is that the consenters are more susceptible to get polio. And this is described a little bit in your book, but I'll just write it really quick. There's basically 2 bits. Consenters are typically wealthier and more likely to get polio. So you might think of sort of wealth as being a confounding factor. The reason why is that they typically live in more sterile environments. The poorer kids tend to live in environments that are a little bit dirtier, and dirtier is actually good for polio. It's good to develop immunity for polio. What happens is that they get exposed at a very low level earlier in life, just kind of dust and stuff in the room, and poorer kids tend to develop natural immunity to polio. Kids that kind of maybe live in smaller families, cleaner environments, they tend to not get this immunity. And so when they go to school, then they tend to be more susceptible when they finally get like exposed to lots of polio out there. Okay? So that's what's really explaining this relationship. That's why the 54 here is bigger than 44. That's part of it, is that the second group is kind of mixed rich and poor kids. The last group is the poorest. So they have some natural immunity, that 44. Same thing here. This last group is the poorest. They have some natural immunity. This group, they're rich kids. They don't have that natural immunity. So my one final thought, sorry for going a little over. Polio does a pretty good job of protecting even the rich kids, is something that you see here, is that if these kids these first group didn't get vaccinated, you might have expected them to be up at 71. Okay? All right, so that's the end of what I have to say about chapters 1 and 2. I'll start chapter 13, chapter 13 on Thursday. So today I will post a handout about that and also your homework assignment due next Monday. You have a double assignment due next Monday and a quiz. Okay, bye.